Keynote by Professor Ferdinand Serracino-Inglott.
So, I'm a vascular surgeon in Manchester, and I'll be talking to you about personalization in the management of aortic aneurysms. So, over the next 10 minutes or so, I'll explain to you, because some of you here are surgeons, some of you are into medical, what an aneurysm is, why we need to treat it, and how we treat it, and how we personalize this treatment. So, what you see here is the aorta, which is the largest blood vessel in the body, which leaves the heart, takes a U-turn, goes down to the level of the belly button, and divides into two. An aneurysm is when this blood vessel increases in size, and it's a bit like a balloon. The bigger it gets, the bigger the chance that it may burst. It contains blood. If it bursts, you bleed. Consequences are catastrophic. So, this is data which shows bigger aneurysm, bigger risk of rupture, and the magic number when we usually operate to treat this is 5.5 centimeters, because that is when the risk of rupture is greater than the risk from the operation. There are two ways of fixing these aneurysms. One is open surgery, which is beyond the scope of this talk, so I won't talk much about that. The other is using keyhole techniques. Now, when we use keyhole techniques in vascular surgery, it's a bit different from the general surgeons. Our keyhole techniques are done through the arteries. So the principle is that you gain access to the artery in the groin, put wires through across the aneurysm, and then put a stent in. The commonest place to get an aortic aneurysm is just below the arteries to the kidneys. And so, usually you have a stent that's in the form of a trousers, so then you can go from the other side to connect it. The whole idea is that blood flows through the stent, no pressure on the aneurysm, no risk of rupture. This is an example here of a stent that's partly open. So that tube the stent is delivered in is around 6.5 millimeters. So where does the problem happen? The problem happens is that not all aneurysms are just below the renal arteries. So as you see here, you've got various shapes of aneurysms, and if you had to put a stent across these, you'd cover these branches, yeah? And that's a problem, because here you've got branches going to the liver, spleen, bowel, kidneys, important organs which are essential to life. So what you do in this case, you make a stent that has special holes to cover the aneurysm and allow perfusion to these arteries. And here is a short video. Oh, how do I make this work? I'm not sure how to get this to work. So, no worries. So, what this video would have shown you is, why can't I just keep going back? That you open the stent here, you align the holes with the vessels, and then you go and get tubes through these holes into these arteries to put connecting stents between this main stent and the arteries here to allow preservation of blood flow to these arteries whilst covering the aneurysm. So there's good data to show that these keyhole techniques are better than open surgery. And if you look at the National Vascular Registry in the UK, you can see that in hospital mortality with complex open surgery is 14%, with complex endovascular is 2.7%. So where does the problem start? So these are 3 different patients, all have aneurysms. And when you look at the visceral vessels here, the branches of the aorta, you can see that they are all in a different place. Yeah. This is a CT scan showing you where in the circumference of the aorta the left renal artery comes out. So you can see in one patient it's over here, in one it's exactly at the side, and one is slightly posterior. So you cannot have a stent that fits all. So what we do in these cases, we take the CT scan, we create a 3D picture of the aneurysm, then straighten the aorta so we can calculate the separation between the various branches. So this would be where your stent lands. This would be the distance from the first artery that goes to the liver and the spleen. And there is the distance from the artery to the bowel. And you also calculate where around the aorta the branch comes out. And you then create a diagram like this with the relation of the arteries to each other. And you go on from that to create your stent. So with your stent, you want an area at the very top that seals in normal artery. Then you've got your vessels there, we call them fenestrations, for the arteries to allow perfusion. And then you make sure those match with the anatomy of the patient. You make sure the clock position also matches. You make sure the diameters of the stent match those of the aorta, because they need to seal. And you then add the trousers bit, and you then create your stents. So these are examples of some of the stents by a company called Terumo Aortic that manufactures them for us with the fenestrations to allow perfusion to the blood vessels. Interestingly, these stents are still all made by hand, so despite all these talks today about technology, they're all hand sutured, and that is a problem because it takes at least 8 weeks to get these stents on the market. So one of the things looking into is if you can have pre-designed stents and then, say, robots that make the fenestrations for you. So one of the things we've worked on in the past a lot is 3D printing of stents, but these are stents to treat blockages. So one of the things we're looking in the future, if we can do that for our aortic stents. Now, another thing is these stents are inserted in a theater, and we use X-ray to see what we're doing. So we don't have nice pictures of the inside of the aorta. What we see is we've got an X-ray machine here with a robotic arm, which then gives us pictures like this. So if you look here, you can see this is the stent. In order to see the aorta, you have to inject dye in the vessel to see the vessels. So you can see the kidney arteries here, for example, and the holes for the kidney arteries are there. And you've got these markers to point to your fenestrations there. So those are the fenestrations to the arteries going to the liver spleen, going to the bowel there. This is what you do when you're putting your stents in. So you've got fine wires there, and then you're advancing stents between the fenestrations here and the artery. So as you can see, it's quite complex and difficult to visualize. So one of the trials we're taking part in right now uses AI to take the CT image and create a 3D picture of the aorta and its vessels, as you can see here, and it marks where the origins of the vessels are. This is a 3D picture, so when you rotate your C-arm, the picture rotates with you, so you can visualize where the vessels are, so you can position your stent. So you can see here a stent being positioned. You can see there the origin of the vessel there, and there is our seat with a wire getting into the stent. Same thing here, going into the renal artery here. So this is all done via cloud and then transferred onto your screen when operating. So we're taking part in this trial, looking to see if this actually does help or just gives us nice pictures. Another thing we're working on, there's another video there, but I'm assuming it's not going to work, is in order to get the stent in place before you fully deploy it and you cannot move it, you need to get wires in all the holes into the vessels, as you can see here. And when you put all these stents through here to get all these, the valves of these seats are not designed to have multiple insertions. So when you have multiple insertions, you get quite a bit of blood loss. Yeah, in fact, that doesn't show it. So one of the things we've done is we've 3D printed a new seat for this, which is still in trials. So we've got a BHF grant for that. I cannot show it yet because it's still waiting IP to reduce blood loss. So to conclude, the future of aortic surgery is endovascular. However, there's still a lot of work to be done because currently the process of making custom stents is still too laborious, and I am certain that in the future we'll see more AI helping us create these devices probably directly from the CT with minimal human interaction, making the process faster. Also, image fusion, which is making the X-ray images more user-friendly, more looking like what you see inside, I think has a potential of making these procedures safer and easier. Thank you.